In this video, we're going to be looking at the last part of the absolute value function that we're going to be changing through the equation, which is the quote-unquote slope, or the slope of each arm of the absolute value function. And so we're going to do that by taking the equation and altering the coefficient that's in front of the absolute value operator. And then what we're going to do is we're going to figure out how we can just look at a graph and get a rough estimate of what the coefficient is just by looking. So that way, even without calculations, we can get kind of a gut instinct for what that should be. So let's talk for just a second about the slope of the absolute value function. Each arm of the absolute value function, and I don't believe that's a technical term, but I'm just using it like this. So I would say that that is one arm, and this is the other, just to have a way to refer to that. You could also call this a right side and a left side based on the vertex, which you'll recall is right there in the middle. But each arm of the graph of an absolute value function has a certain slope. And the neat thing is that whatever the slope on the right side is and the slope on the left side is, they'll have the same number but with opposite signs. This graph that you see right here is the graph of y equals the absolute value of x. No transformation of the vertex, so we don't have any h or k, so the vertex is right at 0, 0. And for this particular function, the slope of this right arm is positive 1, and the slope of this left arm is negative 1. And so we can see that both of those arms have the same slope as far as the number goes. It's just they have opposite signs. One's positive and one's negative. And it doesn't matter which one is positive or negative. We could have both situations. All that matters is that they have opposite signs. Whatever this number is, this number will be its opposite. And so knowing that, we can take a look at how to modify the slope, quote-unquote slope. It's not really slope because we have two different lines that we're talking about and it's two different values, but it gives us an impression of slope. But anyway, we can find that by just adding one thing to our vertex form of an absolute value function, and hopefully you can look at this and see what it is. Now you don't have to write anything just yet until I tell you. This is just a recap of what we learned in the last video. We said that h is the x-coordinate of the vertex, and k is the y-coordinate of the vertex, but we've added something new on this one, a. And now this is the part where you can write this down. A is the slope of the right arm of the function. And so if we know the slope of the right arm, we also know the slope of the left arm of the function, because we know it's just going to be the same number but the opposite sign. So A just tells us what the slope is for that right arm of the function. And now here's why I put slope in quotation marks. We've represented slope with the letter m, but we don't use the letter m here, and the reason being is that this number is telling us more than just a direct slope. It also is giving us information about the other side, and besides, this thing isn't linear, strictly speaking, and so that idea of slope doesn't work as cleanly on this, but we can talk about a as being a type of rate of change. So a gives us the slope of the right side, and if we know the slope of the right side, we know the slope of the left side is just the opposite of that. Now, another thing we can do is, knowing that, we can estimate the value of a based off of what the graph looks like. And I'm going to pull up our friend Desmos here so that we can take a look. What you see right there is y equals the absolute value of x. This equation right here, and you can see it is in green. And I have over here y equals a times the absolute value of x. And right now a is set to 1 so that those two graphs match. But what happens is, as I increase the value of a, as a gets bigger, you can see that the graph gets more narrow, that opening gets skinnier the bigger that a gets. And so if I have a good image in my mind of what the absolute value of x looks like as far as the function goes, if I see something that's more narrow than that, I can make a prediction that the value of a, that coefficient in front of the absolute value operator, it's going to be bigger than 1. If it's equal to 1, then obviously we just have our normal y equals the absolute value of x function. But here's something interesting. As we decrease a, but keep it positive, so still bigger than 0, but less than 1, a fraction, our graph gets fatter, for lack of a better term. It gets wider as it goes out. So if I have a really wide absolute value function, I can predict that a is going to be very small, less than 1, but still positive. Also, if we stop and think about it, what has to happen if a is 0, if we're multiplying by 0? Well, that's right, we get 0 everywhere. So when a is equal to 0, we just get a flat line, and we don't even need the absolute value function to describe that. It's just the line y equals 0. When a becomes negative, and let me go ahead and set that up right here, you can see that the function actually flips upside down. So it looks like a V that's just been turned over on its head, and so it starts to take on sort of this pyramid-looking shape. And then everything we learned just applies. As the numerical value of a increases for the negative, it gets more narrow. And if it's between -1 and 0, it gets wider. And so with this, we can make an estimation as to whether or not we've graphed it correct or if we're looking at the right function, because we have sort of a gut check feeling of what this thing should look like. So now let's practice a few of them. Graph the equation y equals 2 times the absolute value of x minus 1 plus 3. So the first thing I'm going to do, just like yesterday or whenever you watched that last video, the first thing I have to do is find the vertex. So the vertex, I need h and I need k, but I have to remember that I'm subtracting h, so I have to take the opposite of whatever this is. So my vertex is going to be at 1, positive 3. And I can plot that point, 1, 3. And now there's the vertex of my function. This 2 on the outside tells me that the right arm of the function, so the part that goes right from the vertex, is going to have a slope of 2. So I would go up 2 over 1, up 2 over 1, so on and so forth, and now I have that part of the function. On the left side, remember that it's going to have the same numerical slope, but the opposite sign. So over here I need a line that has a slope of -2. That means I'm going to have to, from some point, go down 2 and over 1. So that would be that point right there. And I can plot those where each one is going down by 2 and then over by 1. And I can see that this traces out that nice V shape that I'm expecting. And I can draw a nice, neat little line here so that we have our absolute value function. And remember, if you're drawing these by hand, I do want you to use a straight edge, make them look nice and neat. So all I did was I plotted the vertex, and then I used that slope for the right arm, and then used the opposite slope of that for the left arm, and there you go, there's the function. So let's take a look at another. Graph the equation y equals -1/2 absolute value of x plus 4 minus 1. Now notice about a is negative, so we're expecting this graph to be flipped upside down. It's also a fraction, 1/2, so it's less than 1, but or it's less than -1, or greater than -1, excuse me, and less than 0, so we're expecting kind of a wide graph as well. So let's find our vertex. So our vertex is at hk, so I take the opposite of what's with the x, -4 and -1, and I can plot that point, 1, 2, 3, 4, 1. There we go, there's my vertex. And now I'm going to use this number, -1/2, as the slope of the right arm. So for the right side, going out from the right on this, I would go down 1 and over 2. Down 1 over 2, and I can repeat that as often as need be. And because I am not all that handy with drawing stuff on the computer, I'm going to give myself lots of points. If you just need 2 and you can connect those with a straight edge, go for it. That's no problem. On the right, or on the left side rather, I'm going to have a slope still with a number of 1/2, but the opposite sign. So over here the slope should be positive. So that means I'm going to go up 1 and over 2. That my point would be right there, and right there. And I can see that this is making that V shape. And if I connect those, I'll have my graph of the absolute value function. Just like that. So again, all we're doing is we're reading off the vertex, and we're using this that we know about slope to graph the rest of it, and there's our shape. So now we can go the other direction. What if I give you a graph and I ask you, hey, what's the equation for that graph? Because that's going to happen. So here's what you do. First thing we need to do is find the vertex. That gives us h and k. So in this case, my vertex is at 4, 5. So now I've got h and k. The other thing I need to find is a. I need the slope of the right arm of this thing. So I need to find the slope of this line. And to find the slope of a line, all you have to do is take 2 points. And so I can take that point right there and that point right there, and I find my change in y. My change in y was -3, and I find my change in x. My change in x was 2, and so my slope is change in y over change in x. Let me write that over here. Slope is delta y over delta x, which in this case is -3 over 2. So now I have my vertex, that's h, that's k. I've got this, that's a. I'm ready to write an equation. So I would write y equals -3/2, and that makes sense because this is an upside down from what we would expect from the absolute value function. X minus h, so x minus 4, plus k, plus 5, and now I've written an equation for that graph. Let's try it one more time. Write an equation for the function shown in the graph. First thing we need is, that's right, the vertex. So we find our vertex, and our vertex is at -2, -5. We also need the slope of this right arm, so I need 2 points on that line. I'll take this one and this one. My change is +3 on the y-axis, +1 on the x-axis. So to find slope, remember that's my change in y divided by my change in x. My change in y is 3, change in x is 1, so my slope is 3, and thus a is going to be 3 as well. This is h, and this is k, so we're ready to write this equation. We would say that y equals 3 times x minus h, h is -2, plus k, which is -5. Now, let's back up a step just in case you're wondering where this came from. Remember, my vertex form looks like this. So now that I've found a was 3, the slope of the right arm, I just plug that in. H was -2, k was -5. But there's some simplification that can happen here, and I do want this simplification to happen. Subtracting a negative is the same thing as adding, so I'm going to change that to x plus 2. Notice this is now the opposite of what's there. Plus a negative is the same thing as saying -5, and so I will write -5 right there, and that is my simplified equation for this absolute value function graph. So to sum up, a, the coefficient of the absolute value operator, controls the slope of the right arm, and the bigger a is, the more skinny my graph of the absolute value function is going to be. The other arm, the left arm, will have that same numerical slope but with the opposite sign, and if a is negative, it's going to flip the graph upside down.